Hello again. I got a question to try to explain or talk about the relationship between creatine phosphate, and the NIRS signal. Because there's some interesting relationships here, and so I think it's a good question, and I think it's important to understand the relationship if you're using your NIRS in sports, especially when you get to higher intensity sports, because it becomes creatine phosphate becomes really important. So creatine phosphate is essentially kind of an ATP buffer that lets you, as you use ATP, you can replenish ATP with creatine phosphate. So it's an important kind of a bioenergetic buffer that you need to have, and you need to, as you need to replenish ATP, you also need to replenish PCr, so creatine phosphate, and those things hang together. Now, what's interesting about this is that there's actually quite a lot of research on this, that creatine phosphate recovery, so the resynthesis of creatine phosphate, and then presumably also ATP, which go all hand in hand, they're oxidatively dependent. So they're done through oxidative processes. And I'm going to actually focus on two papers that are going to link these concepts together. The one is by Russell Richardson's group. It's called Skeletal Muscle Phosphocreatine Recovery in Exercise-Trained Humans is Dependent on O2 Availability. That's the title. And in the title, as it says, that it's relating this creatine phosphate recovery and the availability of O2 to recover creatine phosphate. So you need to use O2. I'm going to put some graphs up. So the first graph is from this study, and you actually see creatine phosphate recovery over time. And what you see is that you have two different curves, and the one curve is in a hyperoxic environment, so with extra oxygen, and the other curve is in hypoxic with less oxygen. And you see that the recovery rates actually change. So this is the argument that it's dependent on O2 availability. Okay. What's interesting in the second one that they have is that the time constant. So if you have the time constant of O2 recovery, which is the y-axis here, is very much linked to your intracellular PO2, so your oxygen pressure in your muscles. So the availability of the presence of oxygen, and the more oxygen you have available, the higher the rate of this recovery is. So you're basically directly linking your ability to recover PCR with oxygen that you have available to you to be used in the muscle to do this resynthesis process. Which goes back to the whole point of these oxidative processes are extremely important, regardless of intensity, to reestablish this creatine phosphate buffer. Now, if we consider this importance of oxygen, it's actually not that big of a step to think about why NIRS, measuring muscle oxygenation, would be a useful tool to assess creatine phosphate recovery. And this is where we get to the second paper that's going to link this, and it's a paper by Kevin McCulley's group. It's called Cross-Validation of NIRS Measurement of Skeletal Muscle Oxidative Capacity and Magnetic Resonance, Phosphorus Magnetic Resonance Spectroscopy, so PMRS, which is a tool that you use to measure creatine phosphate. And so we'll put some more graphs up here. What McCulley showed is that essentially your muscle VO2 measured by NIRS, so the rate at which NIRS is showing changes in muscle oxygenation, is very, very similar to the rate of creatine phosphate recovery. Now, if we think about Richardson's work, where he's linking this O2 availability to the rate of recovery of PCR, well, it kind of makes sense that these two things are going to be very similar. And this is what McCulley shows. He shows this further in a nice Bland-Altman plot, where he just shows that the time constant of recovery for your PCr. So basically for your PMRS, so your creatine phosphate curves and what you're measuring with your NIRS are the same. And this is what we want out of it. Now, how does that help us? Well, it lets us know that if we think creatine phosphate is an important measure that we need to understand, especially the recovery of this, for example, in interval training, NIRS can help us think about this in a much more practical way, because you can apply it to your training. So I have a recovery rate of my muscle oxygenation. This is going to be somehow tightly linked to my recovery rate of my creatine phosphate, which I need to recover if I want to repeat my performance. This is also probably studies that I've done at the university here, but also there's a few papers out there too, one by Rob Duffield, this is an Australian group, where you see that if you do passive recoveries, you actually have a better repeat performance than if you active recoveries, especially if the recovery and the time intervals are really short, which kind of links this idea that the less energy you're actually taking up in your recovery, the faster you're going to be able to reperform, which affects this whole PCr recovery rate, just from a practical point of view, to not confuse anyone there. But there's a lot of practical value here. Now, because I don't want to confuse people, we got to nuance this a little bit. And that is that a lot of this work where you compare PCr recovery and NIRS, for example, there's confounding factors, and the more maximal intensity that you go, and this can be either by volume or intensity, so it's those two factors interplay with each other, is the amount of time spent at high intensity and what the actual intensity is. So you actually start creating the relationships becomes more confusing. And if you have Amoxia and you've done interval training, you know this is the case, because you will realize that your muscle oxygenation will recover faster than what you actually feel ready to reperform. And this is true, at high intensities, which is either load or volume, or like duration of not just the intensity, but also the duration of the intensity, the interplay of those two. And the reason for this is that you start metabolite accumulation, okay? And so simply said, for example, if you have a drop in pH, so you get proton accumulation and you have a drop in pH, so you have an acidosis going on, this low pH inhibits ATP resynthesis. So it's going to affect your ability to restore energy parameters. And it's because pH limits creatine kinase function and also PFK, so phosphofructokinase. That's right, PFK, which is rate limiting in glycolysis. So these metabolite accumulations are going to affect these recovery curves. So you need to keep that in your head. So there is this nice relationship that we can use NIRS for to help us understand creatine phosphate and help us understand recovery curves of creatine phosphate, and which is very useful in training. But we need to keep in mind that there's some confounding physiological factors there. So don't blindly follow the signal, but use the signal to help you identify recovery rates, let's say. It can also be expenditure. It helps you think about expenditure or oxygen utilization, right? Expenditure as well, but also the recovery of this. I hope that cleared it up. If there's any other questions on this, there's lots of papers out on this as well, not just the two, but I would recommend reading those two for sure, because I think they do a good job linking NIRS and the creatine phosphate recovery curve and the importance of oxygen utilization and supply to maintain kind of this bioenergetic flux. Thank you very much. And it's happy holidays and Christmas and stuff. I probably will not be making a video again until next year. So thank you very much for everyone that has listened to my YouTube videos, and I hope they've helped people. I've gotten some feedback from people. I tend to make the videos for very specific questions for those people, and I've gotten generally positive feedback. And I'm happy if other people get to watch the videos too, and it helps them. And please, next year, send me some questions again, and I'll do my best to answer them. So happy holidays, Merry Christmas, and all that. and see you in 2019.